Sure. So our next speaker is Wulff, who will be telling us about the integrability for AdS3. Let's see if I remember. Cross S2, cross S2, cross T3. Is that right?
Yes. Okay, so I want to thank organizers for the invitation to speak here. So I'll be talking about integrability of strings in AdS3 cross S2 cross S2 cross T3, and hopefully it'll become clear why I'm picking this specific background in a little bit. And what I'm going to say is based on a paper that appeared a few months ago, 08788, and also on some work to appear. Okay, so let me start with some very general words of motivation for why I'm interested in looking at things like this. So we all know that integrability is a very powerful tool in the AdS-CFT context. In particular, it allows us to compute the spectrum of dimensions of operators exactly in the large N limit. So a very natural question to ask is, how many examples are there of integrable AdS-CFT correspondences where we can exploit these techniques and solve the correspondence? Okay, can we even come up with something like a classification? Now, from the string theory side of AdS-CFT, this would mean that we would have to find all the possible AdS backgrounds and check whether the string is integrable in those backgrounds. Now, clearly that's a very difficult problem, so I don't want to try to do this. Even the first part is too difficult, trying to find all the AdS backgrounds. But what I will do instead is to consider a baby version of this problem by restricting to a certain class of backgrounds on the string theory side. And the backgrounds I want to restrict to are symmetric spaces. And so by symmetric spaces, I mean that the geometry is that of a symmetric space, but I also mean that the fluxes respect the isometries. In general, they do not have to, but I'm restricting to the case where they do. And this baby version of the problem turns out to be doable. And the reason for that is that we can now solve directly the first part of the problem, which is to find the AdS backgrounds. And this is because when we restrict to symmetric spaces where the fluxes respect the isometries, the supergravity equations of motion become completely algebraic. All the terms with derivatives of the field strengths and so on are zero, and we have some set of quadratic equations to solve the parameters that enter this. So this means that it's possible now to classify all the symmetric space supergravity solutions. So we can do the first part of the problem, and then the second part is to analyze the integrability of the string in those backgrounds. Okay. Okay, and since this is a conference on AdS3, I'm going to restrict from now on to the AdS3 case. And so let me write down the complete list of backgrounds. Okay, so there's one background, AdS3, CP2, S2, but it can also be non-compact, so it can be a hyperbolic two-plane times an S1. There's another example which is related to this one, temperature of the S2 or H2 to 0. Of AdS3 times S3 times S3 times S1 that many people in the audience are familiar with. There's also AdS3 S3 S2 H2. The same with a hyperbolic space replaced by a flat torus. AdS 3 times S3 times T4, maybe the most familiar example. And then we have AdS 3 times a bunch of two spheres, where I can replace one of them by a hyperbolic plane. And we have AdS3 to S2 T3, which I will talk more about. And then finally, when we take the curvature of one of the S2s to 0, two times T5. Okay. Well, it comes out by analyzing the supergravity equations. You get some. So the curvatures of these spaces will be determined in terms of the parameters that enter the fluxes, and in some cases it's possible to take some of them negative. But for that, you have to look at the specific example. Some can have only Ramon-Ramon flux. Some can have only an SNS flux, like this example, but most of them have both. And you can't switch one or the other off. AdS3, S3, T4, for example, which we just heard about. No, I'm saying there is, I think only in that, well, in that case, you can have only an SNS flux, but in the other ones, you typically have a mix. Okay, so this is the complete list. So I guess if you're counting the different geometries, it's I think 11 different geometries. These are all the symmetric spaces which have an AdS3 factor and solve the supergravity equations. But now it's interesting to see how many parameters these backgrounds have. So, the parameters are the ones that enter in the fluxes. And now it depends on if I'm looking at type 2A or type 2B. So let's take the first background, S3, CP2, S2, S1. That has one parameter, it turns out, in the type 2A case, but in the type 2B case, there's no such solution. Because there's an SNS flux on that background, on the S1 direction. So if you T-dualize, you'll break, I mean, you can T-dualize, but you will break the fact that you have a symmetric space. Or that the fluxes respect the isometries. In this example, you have no free parameter, and again, there's no solution in the type 2B case, and so on. Here we have two parameters. Here we have two real parameters. This background doesn't exist in type 2A, but it exists in type 2B and has one free parameter. So on. These have one in both. Yes, exactly. I wrote it instead of 0. Yeah. The X means there's no solution, and the dash means there's no parameter, but there's a solution. Right. This has 1, 2. Now this one has. Sorry? When I'm counting the parameters, I'm setting the AdS radius to 1. Yeah, so there's always that, but it's a dimensionful quantity, right? So dimensionless parameters, if you want. This example with 3 S2 factors has 3 parameters in the type 2A case, but there's no such solution in the type 2B case. And now this one gets even more interesting. Here there are several branches of solution. There are several branches with 2 parameters, 3 branches, and then one branch with 3 parameters. But in type 2B, it's less rich, and you have just one branch with 1 parameter and another branch with 2 parameters. When I'm counting the parameters, I'm fixing the radius of AdS if you want to one, or yeah, if you want to call it a parameter, then you can. Right, but if I measure everything in units of the AdS radius, right? I don't count that. Yes, you always have that. Okay, so this case is quite rich. And the last one, I'm not sure you can see, but here there's 1 parameter and no parameter in the 2B case. So you can have, in that case, you can have both F3 and F5 flux. You can have a combination. You can generate one parameter by T-duality, by two T-dualities if you want. But that's why you have two parameters in the 2B case, but you have one parameter in the 2A case. But they're still T-dual to each other. Okay. And then, of course, we want to ask about supersymmetry. And most of these examples don't preserve supersymmetry. No supersymmetry, no supersymmetry. This has 16 supersymmetries, as we know. No supersymmetry. This has 8 supersymmetries, 8 supercharges, 16. None. This can have either this can either preserve 8 superchargers or no or none, and the last one preserves 8. Okay, so that's the list that we want to look at. But and now we want to ask which of these backgrounds, in which of these backgrounds is the string integrable? So that's the final column. For the supersymmetric backgrounds, integrability has already been established. So we know that AdS3, S3, S3, S1 is integrable. But also these other examples that preserve some supersymmetry. But in the other cases, we don't know whether the string is integrable. Yes. Not necessarily, as we will see. The superisometry algebras. Yes. So they're well known. So in general, so this involves D21 alpha squared. This is a limit of that PSU 112 squared. And then these other guys that preserve 8 involve one copy of D21 alpha or PSU 112. Right, exactly. There's no supergravity solution. Yeah, this is the full list of supergravity solutions that are symmetric spaces where the fluxes preserve the isometries. In principle, you could have higher hyperbolic spaces, but you don't get any solutions in 3. Yes, I want to discuss now classical integrability. I will tell you. Okay, so this was only the first step. Now I will focus on this example. Of AdS3, S2, S2, T3. And the reason for that is that, particularly in the type 2A case, I have many parameters and many branches. I also have a solution that preserves supersymmetry, but most of them don't preserve supersymmetry. So this is somehow, this is the richest example. Yes?
Should it be integrable dash question mark? The one that does preserve?
Yeah, the supersymmetric one is integrable, so I could write yes dash. It's just the non-supersymmetric case that's not known. Okay, good. So now we focus on that. So in general, integrability will put some strong constraints on the parameters that appear in these backgrounds. So in particular in this case, we're focusing on. So So we'll put some constraints on these parameters that we have. And a useful set of constraints that I will focus on come from the fact that there should be no particle production in the two-dimensional theory if it's integrable. Which I can just write in general like this. So in particular, I will look at scattering where I have two particles coming in and a different number coming out. Specifically, I will take the case where I have 3 of them coming out. So in that case, I would have some particle production, but integrability requires all those amplitudes to vanish. And that will put some constraints on my parameters. I will be at tree level, yes. You can also ask this question at loop order, but I'm not going to be that brave. I won't need to in this case, it turns out. Yes, well, not immediately, but in the end we'll get there. In this case, at least. Okay, so the strategy is the following. So first we'll expand around some classical string solution. And then we will analyze some 3 scattering. We require 2 to 3 scattering processes to be 0. And that will give us at least some necessary constraints for integrability. And it will be enough in this case. Whether I have what? No, not at this level. No. Well, I don't know. In general, that could be a problem, but we'll bypass it completely with what I'm doing here. Okay, so if you start by thinking about the bosonic string, the only thing that enters besides the geometry is the NS&S3 form flux. So in this case, it takes the following form. So H, which is the field strength corresponding to the B field, which is the thing that enters in the sigma model, string sigma model. It takes this form, some parameter H1 times following. So it's a 3 form. This is the volume form on the first S2. So it's a 2 form, and that's wedged with one of the coordinates, one of the T3 coordinates. And then there's the volume form of the second S2, H2 dx8 plus H3 dx7. Okay, a combination of 2 of the torus directions. And then there's a piece which is just on the 3 torus. Okay, this is the general form of the NS&S3 form flux for this background. Notice there are 4 parameters here, H1 to H4. In general, they are constrained in some way by the supergravity solution, because I said that I have 2 or 3 free parameters only. But at the moment, I'm not going to care how they are constrained. I'm just going to ask what are the conditions if I have this general form. Yeah, but they're all of this form with some additional constraints on H1, 2, 3, 4, which in general are a bit complicated. Let's see. Okay, but in particular, we note that there's no flux on AdS3. A priori, I could have thought that I could put some flux on AdS3, but it turns out it's not consistent with the supergravity equations of motion. I guess I'll have to erase this. Yes, there's both Ramon and SNS flux. But first off, I want to think of just the bosonic modes. So the bosonic strings, I don't care about the Ramon flux. Okay, but because there's no flux on AdS3, it's natural to consider a string solution that lives there. So we will take the long spinning string, the Gubser-Klebanov-Polyakov, it's a string that's spinning in AdS3. And we want to now expand around that solution and look at what the conditions are that come from the fact that all 2 to 3 processes should vanish at tree level. So if I take some light cone type coordinates, which I call Z plus, Z minus, and then there's a third transverse coordinate Z on AdS3, then this solution looks like Z plus, the long spinning string solution looks like Z plus is sigma plus tau, Z minus is sigma minus tau. So I want to expand around that solution. And if you expand you expand the action to quadratic order, you find that this transverse boson Z is massive. While the transverse coordinates that are coming from the rest of the space, so from S2, S2, T3, are massless. So I can simplify things even further if I take a low energy limit and just integrate out this massive boson set. So this gives me the low energy effective action. I'm doing that just to simplify the problem as much as possible. So I'm looking now just at the low energy modes of this long spinning string. And now it's easy to see that the bosonic action consists of 2 O3 sigma models coming from the sphere. So coming from the two S2s, so they will have coordinates x3, x4 from the first S2, and then x5, x6 from the second S2, and then I will have the three T3 directions, which have coordinates 7, x7, x8, x9. And so the action will consist of those two O3 sigma models coupled to these guys, and the couplings between these guys will come from the NS flux, and you will have couplings of the form, I guess I erased it now, but you remember there was a term, some parameter h1. If we get a coupling, one of the torus coordinates to the volume form, pull back of the volume form on the first S2, and that's and similar things from the form of the NS flux. And if I expand this, of course, this gives me some cubic coupling, x7 di x3 dj x4 plus some higher order couplings. Okay? So I will have cubic and higher order quartic and fifth order couplings and so on. They're related in some way to the parameters that I have. No. In general, they're related in some complicated way to all this h1 through h4, and also potentially other parameters that appear in the Ramon flux. But at the moment, that doesn't matter. Okay, so we have some theory. We can write it down completely. There's some cubic couplings and some high ones. So now let's look at some specific scattering. So let's take two of these bosons from the first S2, x3 and x4, and compute their scattering into x5, x5, x7. So remember, this comes from, so these come from the first S2. This guy comes, S5 comes from the second S2, and this comes from the T3. So it's a particular 2 to 3 process that I can compute. But it turns out to be very simple because there's only one diagram. And it involves this cubic vertex and similar cubic vertices that you have. Looks something like this. X5, X5, X7. This internal guy is x6. Okay, so that's the only diagram that I have to compute. And it's quite easy to compute it from the action. And you find that the amplitude is h1, h3 squared, p1 plus p2 minus, in some particular kinematic regime, this factor doesn't really matter. What's important is that the amplitude is proportional to h1 times h3. And you can compute some other amplitudes. For example, if you compute x3, x4 going to x7, x8, x8, so 3 of the torus coordinates, you find something very similar. There's some constant of proportionality there. H1, now H4 squared. Okay, so now we said that for integrability, these things have to vanish, which means that since the momentum won't generically vanish, this H1 times H3 and H1 times H4 has to vanish. Yes. Conformal gauge, yes. Yes. You can do it different ways, yes. You would probably get the same. Here I'm also restricting to the low energy effective action, so I think you get the same. Well, I'm picking a specific solution. I'm taking the long spinning string. Yes. In principle, you can try to do it for some other solution, but here I'm picking a specific one, which is enough. I should get something integrable, because if the full theory is integrable, then whatever solution I restrict to, I should get something which is integrable. I'm assuming that. Yeah. It shouldn't matter what solution I'm expanding around, right? Okay, so in the end, what you find is that H3 and H4 have to vanish. It turns out that H1, here it looks like H1 could vanish, but it turns out that then everything but H4 would have to vanish, but that's not consistent with supergravity, so you get this. Yep. They're massless, yeah, because I've taken the low energy effective action, so I'm just left with the massless modes. Yeah. Well, in principle, it's subtle, but here I don't really care. I mean, I'm doing something very simple, which is just computing some tree-level scattering amplitude in some two-dimensional theory. I expect this to be necessary for integrability, yes. Okay, so two of the parameters in flux have to vanish. Which means that that the form of the flux reduces to this: volume 1 dx7 plus H2 volume 2 dx8. That's all we're left of. We're left with for the NS&S flux. But now it's pretty easy to complete this to a full supergravity solution. For type 2A, you can add F4 flux, which takes the following form. Dx9 plus or minus H2 dx7 wedge dx9. Okay, this is now the full supergravity solution, where I have to restrict the parameters so that H1 squared plus H2 squared is 1 if I set the AdS radius to 1. Okay, so I really have a one parameter family of solution, but I have a plus minus sign here, so I have two branches. And it turns out that if I take the plus sign, I have no supersymmetry, and if I take the minus sign, it preserves 8 supercharges. So there's two branches with one parameter each. One is supersymmetric, one is non-supersymmetric. Okay? So we saw that this condition was necessary for integrability because we needed it for some of these 2 to 3 processes to vanish. But in fact, it's also sufficient because now you can show that this solution is actually T-dual to AdS3 times S3 times S3 times S1, where I view the S3 as a Hopf fibration, so as an S1 fibration over S2, and I do T-duality on the fibers of these S3s. Then I get something of geometry AdS3, S2, S2, T3. And in fact, I can show that I get precisely this supergravity solution. And the 2 branches are accounted for by the fact that when I do this T-duality on the Hopf fiber, I break half of the killing spinners on the S3. But I can do it in 2 different ways. When I do 2 of these, I can, if they have the same orientation, I break the same killing spinners and I preserve 8 of them. But if I have opposite orientation, they break the opposite supersymmetries, which means that the result is that preserves no supersymmetries. So that accounts for the 2 different branches that I found here. Okay, so let me just put up some conclusions. So the most general AdS3 symmetric space AdS3 times S2 times S2 times T3. The most general integrable symmetric AdS3 times S2 times S2 times T3 solution is T-dual to AdS3 times S3 times S3 times S1, which we know is integrable. Okay, so the conditions that I found are also sufficient for integrability because by this T-duality, I can start from this integrable model and I can just T-dualize everything and go to this model and I immediately have the lax connection and everything I need. Okay, so we found that the most general integrable symmetric AdS3, S2, S2, T3 solution is just T-dual to this supersymmetric one that we knew, which also suggests that supersymmetry is playing some role in integrability because even though you can have a non-supersymmetric branch, it's still, the string still knows about the supersymmetry of the dual model. So we still have no examples that are genuinely non-supersymmetric, that are not T-dual to something that's supersymmetric and are integrable. And what remains to do is, of course, to check integrability for the other examples that I listed. And in general, this will involve also looking at scattering of fermions. Here I didn't have to look at any scattering processes involving fermions, but in general, I will clearly have to include them. For example, if only Ramon-Ramon flux, then clearly I have to go and look at involve fermions. Okay, thank you for your attention.
Thank you. So we already had a number of questions, but maybe there is time for a few more.
So let me see if I understood correctly. What you're saying is that on AdS3, S2, S2, T3, you can write down a whole bunch of solutions. And
Yes.
depending on how you pick your flux, you get integrable or non-integrable solutions.
Yes.
Now, do you know what the near horizon limit of what geometry you have to start with to get and take near horizon limit off to get these general
No.
I mean, in the case where it's sort of T-dual to AdS3,
Exactly. The integrable cases you know indirectly through this.
right.
You can also, I think, directly construct the supersymmetric one. You can directly construct as some near horizon limit of some geometry. But yeah, indirectly, of course, you know it through the T-duality. But for the general solution, which has a bunch of parameters, no. I mean, you don't. Presumably, there isn't one.
I mean, because they all preserve the same amount of supersymmetry.
No, no. Most of them don't preserve any supersymmetry. There's only one. There's only this one particular one-parameter branch where I pick this minus sign here. I mean, here I've already restricted to one parameter. Yeah. Yeah. So generically, I had 2 or 3 parameters, and for generic values of this, it's non-supersymmetric. It's only when I restrict to this class where I have only one parameter left, where I pick the sign correctly. That branch is supersymmetric, but it's some very special subset of the general solution.
Any other urgent question? If not, let's thank Linus again. And now we have a break.